Hello, and welcome to Cruising Through Calculus. My name is Alex, and today we're going to be talking about finding the area between curves and finding the volumes of either solids of revolution or volumes of shapes where we know what the cross-section is. Let's dive right in. Our first question says, find the area of the enclosed curves. And then they give us a bunch of equations up here. Y equals negative 3 over x squared, y equals 1, x equals 1, and x equals 4. So when you're doing these problems, the first thing you want to do is a quick sketch of the curve. So let's go ahead and start with y equals negative 3 over x squared. Well, normally, like 1 over x squared would look like kind of a volcano shape. But because it's negative, that would put it down below. So we're going to get a shape that looks something like this. Now you don't have to be perfect with these graphs, but you do need to be reasonably accurate to get the answer, because you have to see what's going on here. The next thing we have is y equals 1. So let's take a look at that. That is just going to be a horizontal line at, well, y equals 1. Then we have x equals 1 and x equals 4. Okay, so x equals 1. Let's see here. Let's put 1, say, right here. Let's put 4, say, over here. Then from 1 to 4, like this. So, can you see the enclosed region we're trying to find the area of? It's right here, this spot. It almost looks like a rectangle if it weren't for this bottom piece here curving away. So, how do you find the area between two curves? Well, generally speaking, the formula you want to use for the area between curves is to integrate the upper minus the lower curve, like this. And that's exactly what we're going to do here. So if you look here, our upper curve is going to be this horizontal line here, 1, and our lower curve is this right here, the negative 3 over x squared. So when we go to set up our integral is going to be 1 minus, and then negative 3 over x squared. The limits of integration, they actually gave us up here, and you can see it here in the graph too. We're starting at x equals 1 and going up to x equals 4. So it's going to be from 1 to 4. Now we have to evaluate this. So let's go ahead and let's see if we can rewrite this a little bit here. First of all, negative negative will be a plus. Let's also take that x squared that's in the denominator and move that up into the numerator. Now what we can do is find the antiderivative. So we have x plus, actually I think we're going to end up with a minus here, because what we're going to have is 3x negative 1 over negative 1. Yeah, so we are going to end up with a minus here. And then we're evaluating this from 1 to 4. So we've got x minus, and then let me rewrite it as 3 over x evaluated from 1 to 4 like that. Now we have to plug 4 in and 1 in and see what happens. So if we plug 4 in, we're going to get 4 minus 3/4. And then we have to take that and subtract what happens when we plug 1 in, which is 1 minus just 3, like this. Okay, so let's see here. 1 minus 3, that's negative 2. We have a negative here, so this is going to turn into a plus 2 over here. Over here we have a fraction, so we've got to deal with that. Let's go ahead and get a common denominator here, which is going to be 4. Looks like we're going to get 16 over 4 minus 3 over 4, which is going to be 13 over 4. So what we're going to have here is 13 over 4 plus 2. Okay, so let's get another common denominator. We have to add 2 to this. So if we're going to add 2 to this, we still need a common denominator of 4. So if I multiply that by 4, we get 8. 13 plus 8 gives us our final answer. It should be 21 over 4, like that. Our next problem starts off the same. Find the area of the enclosed curves. But you'll notice this time we have x equals 2 root y and x equals y squared over 4. So we have them in terms of y instead of x. Well, we can still graph these. In fact, one of the things that you might want to do when you're looking at these is take them and solve them for y. So let's do that. Let's start with this first one here. In fact, let me do this in blue. So this first one here, if we solve for y, I'm going to have to divide both sides by 2. And then I'm going to have to square both sides. And that'll give me my y. This one here, if we want to solve for y, I need to multiply both sides by 4 and then find the square root. So when we find the square root, we're going to get a plus or minus 4x equals y. Of course, the square root of 4 is 2, but that's okay. I'll leave it like that just for now. Now, before we actually graph this, it's important to note that when you're graphing something with a square root in it, you only want that part. What I mean is when we go to graph this, we're only going to graph the positive portion of this. Over here, it looks like a whole parabola, but because it's x equals 2 square root of y, it's going to be just the right side of the parabola. This here is a parabola, it's just a sideways parabola that opens up to the right. And that's where the plus or minus comes in. So we're going to get the top half and the bottom half. So let's go ahead and do a sketch here to see what this looks like. Our first piece here, normally I would draw a parabola. But because of what I said earlier, I'm just going to draw the right side of the parabola. So it's going to do something maybe like this. This over here actually is a parabola. It's just going to be a sideways parabola like this, hence the plus or minus here. So what we're going to get is something that perhaps looks like this. And you can see now that the enclosed region is this spot right here. So that's what we're trying to find the area of. Now, in the last example, I said typically when you're finding the area, you do upper curve minus lower curve. You actually could do that here, but it's going to be easier to do right curve minus left curve. Can you tell that this right curve over here is always on the right and the left curve is always on the left? That's the key for me. Not to mention the fact that they gave us x equals in these problems here. So, if we're going to do right curve minus left curve, our integral is going to be 2 square root of y. There we go. The left curve is the pink one, so it needs to be y squared over 4. That's better. Everything's going to be done with respect to y this time. If we're doing everything with respect to y, you might wonder what our limits of integration are. So what we need to do is figure out what are these intersection points here and here. And specifically, we're going to be looking at the y coordinates because everything's with respect to y. This one I think you can see pretty easily. That's just 0. But what about this one here? Well, in order to figure out what that is, what we're going to do is we're going to come up here and set these two equations equal to each other. So 2 square root of y equals y squared over 4. Let's multiply both sides by 4. Like that. Why don't we square both sides to get rid of that squared root here? So we're going to get 64y equals y to the 4th. Then let's move everything to one side. So y to the 4th minus 64y. Well, here I can factor a y out. That'll leave me with a y cubed minus 64. And now I know what the answer to this is. Y cubed minus 64 is 4. 4 cubed is 64. So that's my top limit here, 0 to 4. All right, now it's time to evaluate this. So let's go ahead and do that. All right, so over here we have 2 square roots of y. In fact, let me just rewrite this. This is going to be 2y to the 1/2. And then I'm going to also rewrite this one. This is going to be minus a quarter y squared, and then dy. This is still going from 0 to 4, but I'm going to leave that out just for now. Okay, so what we need to do here is add 1 to the exponent and then divide by that number. So we're going to get 2, let's see, that'll be 3/2, and then divided by 3/2. Over here, we've got a quarter y cubed over 3, and we are evaluating this from 0 to 4. So all we have to do is simplify this here. So let's go ahead and simplify this. Let's see here. Dividing by 3/2 is the same as multiplying by 2/3. So what we should get here is 4/3 y to the 4/3, or 4/2. And then here we have minus 1/12 y cubed. And this is evaluated from 0 to 4. Now, 0 is a nice number because if I plug 0 in, I'm just going to get 0. So all I have to do is worry about plugging 4 in. So I'm going to do that. Now there's something special I'm going to do on this first one when I plug 4 in. Let's see here, this should be 4 cubed over here. I could just straight up plug 4 in, and that would work, but instead I'm going to write it out as 2 squared. And the reason I'm doing that is because we have 2 squared to the 3/2. And if you have a setup like this, you can multiply the exponents. So 2 times 3/2, well, that's just 3. So this is really just 2 cubed, which means what we have here is 4/3 times 8. Over here we have 4 cubed, which is 64. So this is going to be minus 64 over 12 like this. So all I have to do is simplify this, and we should get our answer here. Of course, 8 times 4, that's 32. Let's see here, over 3 minus, and then let's take a look and see here. That'll be 32 over 6. 16 over 3. So it actually does simplify down, which is nice, because now they have the same common denominator. Now that they have the same denominator, we can actually just subtract these two. So 32 minus 16 should be 16. over 3. So 16/3 should be our final answer. Let's take a look at this next one here. We have y equals x cubed minus 6x and y equals x squared. Well, hey, why don't we start with graphing y equals x squared? That's going to be pretty easy because that's just a parabola. But I don't know exactly what this one looks like. However, with a little bit of work with this, we can figure out what is going on. So let's take that equation and write it down here. Let me do this in blue. In fact, what I'm going to do is I'm going to factor this. And I can factor an x out. So if I do that, I'm going to get x squared minus 6 like this, which means that this will touch the x-axis if we set this equal to 0 at x equals 0 and x equals plus or minus the square root of 6 like this. Now, I don't know exactly where the square root of 6 is, but that's okay. We can approximate it on our graph here. So we know 0 is one of the points. And then let's just say that 6, let's see here. It should be a little bit more than 2. So let's go out 2 units in each direction, and I will draw the graph just a little bit shy of -2 and a little bit more than +2 here, like this. So that's where it touches the x-axis. If you think about the end behavior, a cubic function has arrows pointing in opposite directions, and because it's a positive leading coefficient, that means it's going to be going up like this. So what we're going to have is a shape that looks maybe something like this. So that's kind of interesting. That means that what we have here are 2 shaded regions, this spot here and this spot down here. So that's what we're going to be finding the area of, and you may notice that because there are 2 separate regions, that means we're going to have 2 separate integrals. And that also means we need to know, where do all of these touch? So I do know, or I'm pretty confident, that 0, 0 is one of them, but what's this spot here? And what about this spot up here? Well, what you can do to figure that out is to take these 2 equations and set them equal to each other. So let's do that. Equals x squared. Let's go ahead and subtract the x squared over here. Let's factor out an x. So if we set this particular piece equal to 0, that gives us this 0. That means that this here will give us these 2 answers. And that can be factored. What multiplies to -6 and adds to -1? Well, that's -3 and +2. So now I know where these intersect. It's going to be over here. That'll be -3. Let's pretend that's -3. And then, or excuse me, -2. Oh, yes, that actually works quite nicely, doesn't it? So -2, and then over here, this will be 3. There we go, that's better. Okay, now we need to set up our integral. Well, our integral is actually made 2 integrals. So our first integral is going to be from here to here. That'll be from 2 to 0. Or excuse me, -2 to 0. I keep making that positive in my head for some reason. And then we need to do upper curve minus lower curve. Well, the upper curve is this cubic function here. So that'll be x cubed minus 6x. And then we have to subtract from that the lower curve. So that'll be x squared. Then what we have to do is add our second integral. This is going to go from 0 to 3. And this time the upper and lower curves have flipped. So we have x squared and then minus x cubed minus 6x, like this. So this is the setup right here. Now it's very important that when you write this out that you should write the second piece in parentheses, especially if you have more than one term, because you're going to be distributing this negative sign here. I didn't write the parentheses here because there was a single term, so it didn't really make a difference. I don't have to distribute the negative anywhere, maybe other than just this piece. So let's do this. I'm going to erase a lot of this, take this, put it up here, and then we're going to keep going. All right, so I've taken our answers that we got down here. I wrote them up here. I did take the liberty of distributing that negative sign, so this is what we get here. Let's go ahead and start evaluating here. So, okay, we need to start by finding the antiderivative. So we get 1/4 x to the 4th minus 3x squared minus 1/3 x cubed. And we're evaluating that from -2 to 0. Then we have over here, it'll be 1/3 x cubed minus 1/4 x to the 4th. 6 divided by 2 is 3x squared, and we're going from 0 to 3. So when we plug 0 in, we're just going to get 0, so that's easy. Then we have to plug -2 in. So we have 1/4, -2 to the 4th, minus 3 times -2 squared, minus 1/3 of -2 cubed. Then over here, If we plug 0 in, we're also going to get 0, but because that's at the end, I won't even have to write it out. We'll just plug 3 in. So it'll be 1/3 3 cubed minus 1/4 3 to the 4th plus 3 times 3 squared. Okay, now I've already plugged both of these into the calculator ahead of time because they're kind of not very nice here. And what you get over here is you get 16/3. And then over here what you get is 63/4. Let's see here, 63/4. So the 4 should go here and the 3 should go there. There we go, that's better. Okay, that means that the last thing we need to do is to get a common denominator. So let's go ahead and put both of these over 12. Okay, 16 times 4, I know that one, 64. 63 times 3, that's 189. Okay, so now we just have to do 189 plus 64. We get 253 over 12. And that's going to be our final answer. Our next problem says, find the volume of the solid that results when the region enclosed by the curves is revolved about the given axis. Okay, so this is a solid of revolution type question. That means we're going to be using the disk method, the washer method, or the shell method for these problems. So let's take a look up here, and let's go ahead and begin a quick sketch of our graph. First, we have the square root of x plus 2. That's going to be a square root graph shifted up 2 units, so it'll look like this perhaps. Then we have y equals 2. That's just going to be a horizontal line also going through 2. Then we have x equals 1, so why don't we put 1, put a little bit further than I normally would, just to give us plenty of room here, like this. And then the axis is y equals 2. So we are rotating this around this axis right here. So the region that's enclosed is this little spot right here. And if you can imagine us rotating it around, that's what we're doing, and we're generating that solid. So if you look and think about that, there's not going to be any gaps in between the axis of revolution and the curve up top here. What I'm getting at here is if you see this and there's no gap in the middle, we're going to be using the disk method. So the disk method is going to be pi r squared, like this. That's what we're going to use. And our goal is to figure out what capital R is. So in order to do that, what we're going to do is we're going to draw in what's called a representative rectangle, like this. It always has to be perpendicular to the axis of rotation. The width, or the base of this rectangle, is going to be delta x, so everything's going to be done with respect to x. And then what we have to figure out is what is the distance from the axis of rotation to the top of the rectangle here. So in order to do that, think about it this way. This rectangle is bound by the upper curve and this lower curve here. So what that means is r is equal to the upper curve, which is the square root of x plus 2, minus the lower curve here, which is just 2. So this very nicely simplifies into just the square root of x here. Once we know what r is, we can plug it into here. So let's do that. Our integral is going to be pi, and then let's see here, r squared. So that'll be the square root of x squared. That'll give us x. And then we need to figure out our limits of integration. But that's pretty simple for this one. That's from here, 0, to over here, 1. So 0 to 1. And just to be clear here, r is equal to the square root of x. That means that r squared is equal to just x. So that's why I put x there. So now the only thing left to do is to evaluate this. This is a relatively simple one to evaluate, so let's do it. I'll write it down here. Okay, so we've got a pi on the outside. Then we're going to have to add 1 to the exponent and then divide by that number and evaluate it from 0 to 1. Now if I plug 0 in, I'm just going to get 0, so I don't have to worry about that. And all I have to do is plug 1 in, which is pretty easy because 1 squared is 1. So our final answer is going to be pi over 2. And so that's the volume of the solid of revolution here, if it's revolved around y equals 2. Now the instructions are the same on this problem, but of course we have a bunch of different equations here. And one of the first things I notice is we have x equals. And usually that means you're going to do things with respect to y. So we're probably going to have an integral that's a dy in it. So let's keep an eye out for that. Let's go ahead and start by graphing these. This one here is going to be a sideways parabola opening to the left because of the negative and shifted to the right by 5. So it's going to look something kind of like this. If you're not sure about the shape, you can always solve for y. So for example, you can add the y squared, subtract the x, and then take the square root of both sides. That'll give you a plus or minus, so you'll get the top half and the bottom half of your sideways parabola. X equals 1, that's pretty easy. Just a vertical line right there. We have y equals 0, and then y equals 2. So we have y equals 0 here. We have y equals 2 up here. Okay, I think I can see the region that is enclosed. It's right here. All right, now we are rotating this about the line x equals -1. So let's go ahead and put in x equals -1 over here. And we are rotating it about this right here, like this. So if you can imagine this, take this little shape over here and then rotate it about this axis right here. And when we do that, I kind of have to like swing out around here, which means there's going to be a gap in the middle here. If there's a gap in the middle here, that means we're going to be using the washer method. So the washer method is pretty similar to the disk method, but it's got one extra part to it. It's going to look like this, r squared minus r squared. Except in our problem, we're probably going to have a dy here. So in fact, let's take a look at that. So this is our enclosed region here. Anytime you're using the disk or washer method, you want to put in a representative rectangle, which is perpendicular to the axis of rotation. We are going to get a dy here. That's going to be the width of our little rectangle here. So it is going to be with respect to y. Now, here's the tricky part. What we need to do is find the distance from the axis of rotation here to the outermost part of our rectangle. So that's going to be this part right here. That's capital R. Then we need to find the distance from the axis of rotation to the smaller part of the rectangle. That's going to be little r. So once we find big R and little r, we can plug them in, and then we can evaluate and get our answer. Big R, can you see how big R, if you think about this rectangle we drew in here, it is bound by this sideways parabola and then goes all the way over here to the axis of rotation. So our parabola is -y squared plus 5, and we're going to subtract -1. We're really just doing kind of like right curve minus left curve. So we get -y squared plus 6. That's capital R. Then we need little r, and that's just the distance bound by this curve and this curve here. So 1 minus -1, or just 2. Can you see how this distance is always 2, because these are just two straight lines? Okay, this is great, because now that I have big R and little r, we can plug it in. So let me plug it in down here just to see what things are going to look like. We're going to get pi r squared minus r squared dy. Capital R is -y squared plus 6. Little r is just 2. And now our limits of integration, these have to be with respect to y. So we're going to start here at 0, and we're going to go up here to 2. 0 to 2, like this. All right, now we have to figure this out. So let's take this, let's write it up here, and let's keep going. All right, it's time to see if we can evaluate this here. So here's what we're going to do. First, I'm going to take this and expand the whole thing. So we're going to get -y squared plus 6 times -y squared plus 6, and then this will be -4 out here. Okay, so let's see what we get here. We're going to get y to the 4th minus 6y squared minus 6y squared plus 36, and then -4. Okay, so I know what we're going to get. We're going to get pi here, then we're going to get y to the 4th minus 12y squared, and then 36 minus 4 is 32. Now we can start evaluating. So let's start with this. We're going to get 1/5 y to the 5th. Let's see here. That'll be divided by 3, so that'll give us a 4 there, plus 32y, evaluated from 0 to 2. Okay, now, plugging in 0 is great, because that's just going to give me 0, so I don't have to worry about that. But I do have to plug 2 in, so let's see what happens. We get 1/5, 2 to the 5th, minus 4 times 2 cubed, plus 32 times 2. Okay, let's see here. That's going to be 32 over 5 right here. That'll be 8 times 4 is 32, and then that'll be 64. So really all we have to do is get a common denominator and add these together, and we should be good to go. So what is our common denominator going to be? Looks like it's going to be 5. So I can leave the first piece, 32 over 5. Then all of these need a 5 in them. So 32 times 5 is 160. 64 times 5 is 320. That means that all I have to do is just add these together. So 32 minus 160 plus 320 is 192. So our final answer is going to be 192 over 5. And then let's not forget that this whole thing is being multiplied by pi here. So I didn't write this in like I should have, but there needs to be a pi here and a pi there and a pi there and a pi there, and finally a pi at the very end here. So let me just kind of add in all of those pi's that I neglected to add in. Need a pi here. There we go. And there's our final answer. This next problem says, use the method of cylindrical shells to find the volume of the solid that results when the region enclosed by the curves is revolved about the given axis. Okay, so we have to use the shell method this time. Let's start by doing a sketch of our graph here. So first, we've got the square root of x plus 2, which is just a square root graph shifted up by 2 units. Then we have y equals 2, so that's going to be a horizontal line, also going through that same point. We have x equals 4, and we also have x equals 5 here. So let's do this. Let's put 4 here, and let's put 5 over here. Now x equals 4 is going to be right here, so that means that this is the region that's being enclosed here. And then we're going to rotate it about y equals 5, so that'll be over here. That's where we're rotating this about. Okay, so this shape here is going to be rotated like this. Now, when you're using the shell method, what you want to do is you still want to draw in a representative rectangle, but this time you want it to do parallel, like this, parallel to the axis of rotation. Now, when we do this, what we're going to get is a delta x here, because that's going to be the width of our rectangle here. So we're going to do everything with respect to x. And then here are the things we need to find. We need to figure out what is the height of this rectangle. We'll call that h. And then we need to find the distance from the axis of rotation here to the center of our rectangle that we drew in. And I'm going to call that capital R here. So if we can find h and r, we've basically got it made. So let's start by figuring out what r is. Well, r is going to be this horizontal distance, starting from here and then going over to here. But since we're starting over here, what we're going to have is 5 minus y, like this. That's what r is. H is going to be the height of this rectangle, which is bound by the top curve and the lower curve here. So the top curve is the square root of x plus 2. The bottom curve is just 2. So we're just going to get the square root of 2, square root of x plus 2 minus 2, which is just the square root of x. Now that we know these things, we can plug it into the shell method integral formula. So let me write out the formula here. It's 2 times pi, the integral from a to b of r h dx, like this. And we figured out what r was, and we figured out, oh, oops, I made a mistake here. I said this was 5 minus y. I guess my mind was stuck in y land. It's 5 minus x, because we're finding the horizontal distance here. That makes more sense, because everything has to be with respect to x here. Now that I have that fixed, we can plug everything in. So what are we going to get? We're going to get 2 times pi. Then r is 5 minus x. Let's see here. H is the square root of x. And our limits of integration are going to be from here to here, 0 to 4, like that. So that's what we have to evaluate. So let's do this. I'm going to take this, I'm going to write it up here, and then we're going to keep going. All right, so I've taken that, written it up here. It's time to evaluate. First, let's take this x and make this x to the 1/2 here. And then let's go ahead and distribute out. So let's see what we get when we do that. We're going to get 5x to the 1/2 here. And then all we have to do is add the exponent. So 1 plus 1/2 is 3/2. Like that. Perfect. Now we can go ahead and evaluate this limit here, or excuse me, this integral. So let's go ahead and add 1 to the exponent and then divide by that number. So we got 5x to the 3/2 divided by 3/2. Let's see here, if we add 1, we're going to get 5/2 over there. So that'll be 5/2 divided by 5/2. And then we're evaluating this from 0 to 4. So let's continue to simplify this a little bit. We've got a 2 pi on the outside. In here, dividing by 3/2 is the same thing as multiplying by 2/3. So that means 5 times 2. This will be 10/3 x to the 3/2. This will be 2/5 x to the 5/2, evaluated from 0 to 4. Okay, now, plugging in 0 is easy. That's just going to give us 0. Always be happy when you have 0 in one of these problems. Now we have to plug 4 in. So let's do that. Now, I'm actually going to do something here. That'll seem a little random at first, but instead of just straight up plugging 4 in, I'm actually going to plug 2 squared in, like this. Because 2 squared is 4. And more importantly, if you have a setup like this, you can multiply the exponents together. So 2 times 3/2 is just 3. 2 times 5/2 is just 5. So what does that mean? Well, that means that we're going to get, let's see here, that'll be 2 cubed, which is 8. 8 times 10 is 80/3. Over here we have 2 to the 5th. Let's see here. 2, 4, 8, 16, 32 times 2 is 64/5. So all I have to do now is get a common denominator. So let's go ahead and do that. It looks like it's going to be 15. 15. Okay, so that means I need to do 80 times 5, which is going to be 400. And then we need to do 64 times 3, which I don't know that off the top of my head. So let me take a look over here. 64 times 3. 192. Okay, we're basically done here. All we have to do is 400 minus 192, which is 208. Then we have to take 208 and multiply that by 2. So that's going to be, let's see here, that'll be 416 is what we should get. So our final answer, let's see here, where to write it? I guess I'll write it right here. 416 over 15 times pi. That's it right there. For this problem, it says to find the volume of the specified solid. And they've told us all about the solid here. It says the base of a solid is the region enclosed by y equals 4 and y equals x squared. Cross-sections perpendicular to the x-axis are semicircles. Okay, so when we do these problems, you do want to do a sketch of the graph. So let's go ahead and do that. That's y equals x squared, let's say. And y equals 4 is just a horizontal line up here, like this. And then, importantly, it tells us that the cross-sections are perpendicular to the x-axis. So here's our x-axis. Perpendicular means like this. So you want to draw a straight line perpendicular to the axis, the x-axis that is. Now, here's what I'm going to do. And this is why I drew this over here, because we're going to change our perspective a little bit, and we're going to pretend like, say this was drawn on a piece of paper, and we're putting the piece of paper kind of down on its side here. You can see everything is the same here, but here's why I'm doing this. It's because each cross section is a semicircle. So I'm going to take this line that we drew here and I'm going to draw a semicircle, which is just half a circle like this. So this solid that we have is just composed of a bunch of semicircles if you take a cross section perpendicular to the axis. What we need to do is we need to find the area of this shape right here. So what we're going to do is we're going to call this length here S. And there actually is a formula to find the area of a semicircle if you know the diameter of the semicircle. Okay, so the area of a semicircle with a diameter that we're calling S is actually pi over 8 S squared, like this. There we go. So what we need to do is find the area of the shape, and that means we need to know what S is. And we can figure out what S is by coming back here and looking at this. S must be the region, you can see that S is bounded by the upper curve here and this lower curve down here. So the upper curve is y equals 4, so it's just going to be 4. The lower curve is our square root, so minus x squared. So that means that the area of this shape is pi over 8, 4 minus x squared, and then squared, because it has to be s squared like that. So once we know the area of this shape, we can actually find the answer, which is to find the volume of the solid, because we can integrate all of these areas together and add them up. So what we're going to do is do the integral of pi over 8 s squared. And we already know what s is. It's going to be 4 minus x squared. We do have to square that like this. Now what we need to do is figure out what are the limits of integration. Well, that's going to be where this line crosses this curve. That's going to be 4 equals x squared, which is pretty easy to solve. X is plus or minus 2. So that means our limits of integration are -2 to 2. So let's go ahead and see if we can evaluate this. There's a couple things I'm going to do here. First of all, what I'm going to do, so let's go ahead and solve this. There's a couple things I'm going to do here. First of all, notice that this is symmetric about the y-axis. That means that this is an even function we're dealing with. And instead of going from -2 to 2, what we can do instead is go from 0 to 2 and double our answer. So if we double our answer, 2 times pi over 8, we're going to get pi over 4. Then I'm going to take this piece here and I'm going to expand it. So we're going to get 16 minus 8x squared plus x to the 4th. And now we can start evaluating. So we're going to get the pi over 4 on the outside. We've got 16x minus 8 thirds x cubed plus 1/5 x to the 5th. And we're evaluating that from 0 to 2. Now, 0 if I plug in is just going to give us 0, so I have to plug in 2. So we have pi over 4, 16 times 2 minus 8 thirds times 2 cubed plus 1/5 2 to the 5th, like this. All right. So I plugged this into a calculator here, and what I ended up with is 64 pi over 15. And so that is our final answer. Let's go over a summary of everything that's happening when we're trying to find the volumes of solids of revolution. First, what you want to do is sketch a graph. That's always the first thing you want to do. Then figure out which method you're using. If you're going to be using the disk or the washer method, you need to put in a representative rectangle which is perpendicular to the axis of rotation. Then, depending on which one you use, you need to find big R and little r. Big R is always the distance from the axis of rotation to the outer part of the rectangle, and little r is the distance from the axis of rotation to the lower part of the rectangle. You only need to worry about little r if you're using the washer method, and you'll plug it into this formula here. Otherwise, you'll just find capital R and plug it into this method here. Now, when you're using the shell method, you need to put in a representative rectangle which is parallel to the axis of rotation. And then there are two things you have to find. You do have to find R, capital R, just like these ones up here, although this one is the distance from the axis of rotation to the center of your rectangle. And then you have to find H, which is the height of your rectangle, which is almost always bound between two curves. If you are finding the area bound between two curves, you're going to use one of two formulas. Either you're going to find the integral of the upper curve minus the lower curve, or the integral of the right curve minus the left curve. It really just depends on the problem you're working on. Sometimes one is definitely easier than the other, or the instructions will specifically say to use one or the other. Now, if you're doing upper minus lower curve, everything should be in reference to x. So the integral should be a dx, and your limits of integration should also be with respect to x. On the other hand, if you're doing right minus left, everything is going to be with respect to y this time. So you kind of have to flip everything in your head and think about everything in terms of y, including the limits of integration. If you're finding the volumes of solids where you know the cross-section, you need to know these formulas for the cross-sections. Square, rectangle, and isosceles where s is the leg of the triangle, and isosceles where s is the hypotenuse of the triangle, an equilateral triangle, and a semicircle. Your goal in these problems is to figure out what s is, which is almost always going to be bound between two graphs, an upper and a lower graph, or a rightmost and leftmost graph. If you found this video helpful, you might consider checking out my website, which is linked in the description below. You'll be brought to Infinity Learning Academy, where you can find Cruising Through Calculus. At Cruising Through Calculus, we have over 100 videos and documents to help you get through your calculus class, including videos for each topic, practice problems, and full video solutions for those practice problems. I hope to see you there, and together we can cruise through calculus.